Imagine trying to time a lightning bolt with a stopwatch. Sounds impossible, right? Now picture scientists attempting something even more challenging. Measuring the speed of light. From Galileo's lanterns to today's cutting-edge lasers, we're about to embark on an incredible journey through time and space. We'll meet brilliant minds who pushed the boundaries of human ingenuity and discover how their work laid the foundation for everything from Einstein's theories to the smartphone in our pocket. Get ready to see the world in a whole new light. Our story begins in the early 1600s with Galileo Galilei. He used common sense in the way we would like to approach measuring the speed of light. Assuming we were to measure the speed of light, we could have a friend stand on top of another distant building at night with instructions that, when he sees a torch signal from us, he is supposed to immediately signal us back with his torch. Similarly, Galileo and his assistant stood on separate hilltops about 1 mile apart with lit lanterns. Galileo covered his lantern, and immediately his assistant covered his upon seeing the darkness. Galileo hoped to measure the delay to estimate the speed of light, but little did he know at that time that what he was attempting to measure could complete 7 rotations around the Earth in 1 second, so the difference of a mile between 2 hilltops was negligible. A speed so fast that even the cowboys from the Wild West would not have been able to help him with their lightning-fast responses. And so, the speed of light was treated as instantaneous for the next few decades. Fast forward to 1676 when Danish astronomer Ole Romer continued the work of Galileo to measure the speed of light with a recently invented telescope from 1608, which was improved by Galileo himself in 1609. Romer observed the eclipses of Jupiter's moon Io, noting that the eclipses seemed to occur later when Earth was farther from Jupiter and earlier when Earth was closer. By comparing the times of these eclipses at different points in Earth's orbit, Romer calculated that light took around 22 minutes to travel the diameter of Earth's orbit, about 300 million kilometers. Using his estimations, Dutch scientist Christian Huygens was the first to calculate the speed of light, arriving at a value of about 211,000 kilometers per second. The actual speed is about 300,000 kilometers per second. The discrepancy was due to slight inaccuracies in Romer's estimate of the maximum time delay and an imprecise measurement of Earth's orbital diameter. Remember, at that time it was still believed that the Sun revolved around the Earth. Romer proved many philosophers wrong who believed that light traveled instantaneously. But who would have questioned a man with a telescope back then? A few who still remained skeptical were silenced by another man, James Bradley, with barrels loaded with lenses in 1727, by observing a phenomenon known as stellar aberration. Stellar aberration is just a fancy name for the apparent shift in the position of stars, due to the combined motion of the Earth in its orbit and the finite speed of light. As Earth orbits the Sun, its direction of motion is constantly changing. Light takes time to travel from stars to Earth. Due to the combination of Earth's motion and the finite speed of light, the direction from which the starlight appears to come is slightly different from its actual direction. This creates an apparent shift in the star's position. It was earlier believed that the Sun revolved around Earth. Bradley's discovery of stellar aberration provided strong evidence for another model of the solar system, which placed the Sun at the center, with the planets, including Earth, rotating around it. He used observations of the angle of aberration, measured to be 20.5 arcseconds, using a telescope attached to a chimney and a screw and plumb line for its alignment. The speed of the Earth around the Sun in its orbit was also known to be 30 kilometers per second, thanks to Kepler's laws, which provided the relative distances of planets from the Sun. Observations, such as transits of Venus and the parallax of Mars, helped estimate the astronomical unit, also known as the average Earth-Sun distance. By using the angle from stellar aberration and the Earth's speed, Bradley estimated the speed of light to be roughly 301,000 kilometers per second, using just geometry. This was quite impressive for his time, marking the first quantitative estimate of the speed of light. Similar to how an hour is divided into 60 minutes, and then each minute is further divided into 60 seconds, making 3,600 seconds in an hour, a circle is divided into 360 degrees. Each degree is further divided into 60 minutes of arc, or arc minutes, and each arc minute is divided into 60 arc seconds for more precise calculations. Thus, every degree has 3,600 arc seconds, and the entire circle consists of 360 multiplied by 3,600 arc seconds. This works like when we are standing in rain, and it feels as though it is coming directly down on us. But if we are moving, It feels as though it is coming from the front at an angle. Thus, by using our own speed and the angle at which the drops of rain appear to be hitting us, we can estimate the speed of the rain. Analogy-wise, the angle from stellar aberration acted like the angle at which rain is hitting us, and the Earth's speed was used as our own speed. In this analogy, the rain's speed itself represents the speed of light approaching us. 100 years later, speed of light measurements saw their golden age in France. Hippolyte Fizeau, who measured the speed of light in 1849, and then Léon Foucault, who measured it more precisely in 1862. Both of these were alter egos, who were born days apart in 1819, wanted to pursue medicine but ended up in physics, and then working in a similar area of physics. But they cannot take the entire credit for the first measurements of the speed of light. They received guidance from François Arago, a prominent French physicist, mathematician, and astronomer known for his significant contributions to the fields of optics and electromagnetism. Arago lived between 1786 and 1853 and shared the idea of mechanically measuring the speed of light with Fizeau and Foucault around 1844. Arago was another genius of the time and a celebrated scientist. Earlier in 1838, he suggested using a high-speed rotating mirror to measure the speed of light, which was not taken seriously by his fellows. He also wanted to compare the speed of light in air and water to test another popular but incorrect theory of that time, the corpuscular theory. In 1843, he first attempted to measure the speed of light. The idea was to reflect the beam off a rotating cylindrical mirror with 8 or 10 faces. The initial apparatus could hit up to 2,000 rotations per second, but they needed more speed. Michelson seemed to get this working even at lower speeds with a few modifications, as we will see later. Arago observed that the shaft could attain even 8,000 rotations per second if the mirror was not mounted on it. He lost his eyesight the same year and discontinued experimenting. He seemed to have communicated the same to Fizeau and Foucault. For some time, Fizeau and Foucault worked together, but they had a fallout around 1845. In 1849, Fizeau measured the speed of light, and in 1850, Foucault confirmed that light moves slower in water. In 1853, when Arago died, he would have finally been able to rest in peace, as both of his experiments were complete. Isn't it exciting that Arago lost his eyesight, but did not lose hope? So was it the success of Fizeau, Foucault, Arago, or us? Scientists are simple creatures, running after simple yes or no answers, sometimes for years. Fizeau and Foucault were also gifted minds of the time and would have possibly received a Nobel Prize if that had existed back then. But how did they make a machine that was even faster than the speed of light back then? Or at least acted faster? And recall, even Arago's astonishing 2,000 rotations per second were not sufficient to measure it earlier in 1843. A speed of 2,000 rotations per second means 120,000 rotations per minute. In comparison, Dyson, the technology company, received its patent for a motor with 100,000 rotations per minute in 2009, which was used in their hairdryers a few years later. Fizeau brought an ingenious approach in 1849 to use mechanics to measure the speed of light for the first time on Earth, which previously could only be estimated using celestial bodies. But could the machines be fast enough? Even at that time, indeed, they could, as the calculated speed through this first-of-its-kind experiment was just higher by 4.5%. Fizeau conducted his experiment to measure the speed of light by sending a beam of light through a system that could create and measure time delays. He utilized beam splitters, or a half-silvered mirror, to split an incoming beam originating from a lamp. But how did divide and rule work for him? The light would come to this modified part of a telescope and would be reflected towards the second modified telescope after hitting a reflector placed in its path. Some part of the beam would be allowed to continue on its original path, thus effectively splitting the beam into two parts. The modified telescope near the lamp also had an eyepiece. Let's call this location point A, where the telescope with the eyepiece is located. Part of the beam would go in this direction, towards the second modified telescope. On this path, he placed a rotating cogwheel with 720 teeth. To prevent the light beam going on this path from escaping without his control, Fizeau placed a concave mirror at the far end of the second telescope. He thought 8,633 meters would be a good number. Maybe he had a 4-digit lucky number. Anyway, his personal choice. Some prefer 7, and even AI has its preference as 42. but I had to leave all assumptions aside upon knowing it was just the distance between his parents' house in Chorezny, where point A was, and a telegraph office at Montmartre, where the second telescope was kept. The distance was probably estimated from a detailed plan for the region consulted with Auguste Félix Broussard, the chief architect of the Paris prefecture. I referred to original research papers in journals around 1849 and 1850, Arago's Popular Astronomy, and biographies of Fizeau and Foucault, to have an accurate understanding of the methodology used. The beam coming from Choreznes to Montmartre would change its direction from Montmartre to Choreznes after its brief meeting with the mirror inside the second telescope, and it would gravitate back towards Fizeau, who would be eagerly waiting for it at Choreznes with a warm heart. However, upon returning to the point of split on the reflector kept in the first telescope, where its direction changed after splitting, it would have to pass through a difficult test set by the splitter, and only the portion worthy of meeting Fizeau would be allowed to pass through, while the remaining would be reflected back to the eternal fire of the lamp. The portion reaching the eyepiece would result in increased intensity of light at the eyepiece. As the master of the speed of the cogwheel, Fizeau controlled the speed of the cogwheel to see an eclipse occur, and again a speed at which the point, which is star-shaped, shines again. Here, I have a slight disagreement with the details explained in this. In this setup, all publications describe this to be a complete eclipse, which I do not think is possible. The current explanation on various websites mentions that the reflector used to change the direction was a beam splitter or half-silvered mirror. I checked in the 1849 paper in Revue Scientifique et Industrielle, which is a French name meaning Scientific and Industrial Review, Arago's Popular Astronomy, and Life and Science of Léon Foucault, by William Tobin. They describe it to be a transparent glass inclined at 45 degrees. However, the biography of Fizeau by James Lecoq mentions it to be a semi-transparent mirror. But in the case of any of them, be it a beam splitter, half-silvered glass, transparent glass kept at a 45-degree angle, or a semi-transparent mirror, the light falling on its surface will slightly bounce on both sides. Incidentally, this will fall on the line of observation from the eyepiece and will prevent the eclipse from appearing completely dark. I assumed this to be true and wrote the script for this video first, only to realize none of the current texts were supporting me on this interpretation. Then I checked the original papers, which were in French, including Arago's Popular Astronomy, originally named Astronomie Populaire, and biographies, but all those also showed a complete eclipse. That is why I tested it myself using my glasses with a laser. As you can see, without glasses, light is going straight. When we introduce glasses, we see the reflection, which would be similar to the light beam sent to the second telescope, but a large part of the beam would pass through directly like this. And here on this surface we can see what I was mentioning. This slight scattering results from an uneven surface, and probably also due to impurities and other particles. These are some of the costliest glasses, and are made with the best technology available today. The glass that would have been used by Fizeau 200 years ago would be no match for current manufacturing technology, and possibly would have had more scattering. But that makes me wonder what I am missing, as all of them said complete eclipse. This is a major reason that will affect the accuracy of observation, which we will see after understanding the working of the machine. The setup of the instrument might already be raising a question in our brain. Other than sounding like a fancy grooming setup of Fizeau with fancy lights, mirrors, and lenses, how would it actually help him measure the speed of light? And what if he just wanted to have a finer shave at night? Let's revisit the path of the light beam going from Choreznes to Montmartre. Upon its return, the beam would take exactly the same path, but the total distance it would travel would be double of 8,633 meters, which is 17,266 meters. At the same time, the cogwheel is also rotating. Fizeau kept on increasing the speed of the cogwheel up to a level where the light beam going through the gap is blocked by the teeth of the cogwheel. He found that at 12.6 rotations per second, the intensity of light was lowest at the eyepiece. As mentioned, the texts mention this to be completely eclipsed. This meant the returning light was completely blocked by the next immediate tooth coming after the gap. Since there were 720 teeth, an equal number of gaps of the same size would have been there, and the light passed from each gap was blocked by the tooth coming after it. By following the same logic, if we double the speed from 12.6 rotations per second to 25.2 rotations per second, the light beam passing through a gap would be met by another gap just after the initial gap from which the light beam originated. The same was also confirmed when Fizeau found the intensity of light to be highest, which has been mentioned as shining like a star in Arago's Popular Astronomy, as shown here. He further tripled the speed, and found that the light at the eyepiece again went to its lowest level, as the light was being blocked by the second tooth after each gap. Again, as described by the books, it was an eclipse and totally dark. By the magic of mathematics, Fizeau estimated the speed of light to be 315,300 kilometers per second, which was about 4.5% off the current acceptable value, but the best at that point in time. If we observe closely, it is difficult to visually tell when the light is at its dimmest level and when it is at its highest level. This probably cost him a lot of accuracy, as every 0.1 rotation of the cogwheel impacted the speed of light measurement by 0.4%. In other terms, if his observed rotation speed had been 1 rotation less than 25.2 per second, his speed measurement would have been 4% more accurate. The error in the speed would have only been 0.5% instead of 4.5%. Other scientists observed this and tried to improve their experiments by having a mechanism of a yes or no type of detection, rather than measuring a degree of intensity, which can be subjective. For example, if the light is visible, then it's a yes, or by observing the shift in the location of the impression. Let's recap. Fizeau created a mechanical timer using an ingenious method by dividing the continuous beam into multiple smaller pulses. I personally feel that if he had used a cogwheel with fewer teeth but a higher rotational speed, such as 72 teeth instead of 720, but at 10 times the rotational speed, he would have obtained a better estimate, reducing the error he saw. Remember, even Arago achieved a speed of 2,000 rotations per second at that time. Foucault did 2 experiments with the speed of light. The first one was in 1850, which proved that the speed of light is slower in water. And the second one was in 1862, which measured the speed of light with much more accuracy, using an improved version of his earlier apparatus with multiple reflecting mirrors. The earlier mechanism had 2 arms on 2 sides of a light source, one arm for air and another with a 3-meter water tube to assess the speed in water. The common images we see on the internet now are of this earlier experiment, which did not measure the speed. Even in some forums, there are doubts that the speed in water was not compared along with the air, and they question the placement of both arms, but both experiments seem to be completely plausible. This is the 1850 setup where the beam originates from here, goes to this rotating mirror, and then to this concave mirror, which concentrates the beam back at the rotating mirror. Since the light would take some time to return to the rotating mirror, the mirror must have moved a little, which would shift the impression of the returning beam slightly. This second part had a 3-meter-long water tube, which superimposed its impression on the image from this first concave mirror. So the normal impression would look like this for air, without any rotation. As we can see, there is a vertical line, which was an actual wire on the light source. He etched a line on the eyepiece for comparison to observe any change in the impression of the wire at the light source. In order to visually differentiate between the air and water, he covered the upper and lower portions of the first concave mirror, and the impression on the eyepiece looked like this. When the mirror is not rotating, the impression of the beam returning through air and water looked like this. When the mirror was rotating at over 600 rotations per second, the deviation on the eyepiece was seen to be around 2 to 3 parts of a millimeter, which looked like this. To measure the speed, this needs to be accompanied by a reference scale and a greater distance for better measurement and accuracy. He added these in the 1862 version, which looked like this. By adding a few more mirrors, the total distance became 40.4 meters. At the reticle, the distance between 2 lines was 1/10 of a millimeter. Here is a small note on the reticle. The French version of the biography of Léon Foucault seems to have interchanged the placement of the reticle and the micrometer in figure 14.5, whereas the English translation of the same, mentioned in figure 13.5, seems to have correct placement of these. The mirror was rotating at 400 rotations per second, and he took multiple measurements and estimated the speed to be 298,000 kilometers per second, with a margin of plus or minus 500 kilometers above or below this estimated value. Let's revise what we learned from the experiment of this another genius of that time. A rotating mirror can give more accurate results even at much shorter distances. This also implies that at longer distances, it would possibly have been near perfect. Also, projecting the returning beam on another surface, preferably on a scaled one, can dramatically improve the execution and accuracy of the experiment. In case the beam had been stronger and he had projected it on an even larger screen, he could have possibly obtained more refined results. Albert Michelson, known as the finest experimental physicist of his time, gave the most precise estimation of the speed of light as 299,796 kilometers per second, with a variation of just 4 kilometers per second in 1926. Before we move ahead, here's a question for you. What is the medium in which light travels? For example, sound travels in various mediums and becomes faster in denser mediums. As you may already be aware, light and other electromagnetic waves don't need a medium to travel. In fact, thanks to Foucault's 1850 experiment, we now know it moves slower in other mediums, such as water through which it can pass. Even up to 1887, scientists believed light traveled through a medium called ether, but why only up to 1887? Because between April and July 1887, Michelson teamed up with Morley to study the impact of ether. This experiment is known as the Michelson-Morley experiment. It was an attempt to measure the motion of the Earth relative to the luminiferous ether. This is one of the most renowned negative experiments in physics, and Michelson was more known for this. A negative experiment in physics is one that fails to produce the expected or predicted outcome. While this might seem like a failure, these experiments often play a pivotal role in scientific advancement. Their experiment concluded that ether does not exist, and light does not need any medium to travel, unlike sound. Earlier, in 1865, James Clerk Maxwell's equations unified electricity and magnetism, predicting the existence of electromagnetic waves that travel at a constant speed. This negative result of the Michelson-Morley experiment in 1887, along with James Clerk Maxwell's equations, led to the development of Albert Einstein's theory of special relativity, which postulates that the speed of light is constant in a vacuum for all observers, regardless of their relative motion. Remember, we use the word postulates here, and we will have a detailed discussion on it in later videos. Michelson was also credited with the invention of the interferometer. The interferometer is a device that helped us accurately measure the speed of light decades later, and, in the year 2015, the existence of gravity waves. In 1907, Michelson became the first American to win a Nobel Prize. It is not an exaggeration to say his contribution to the progress of science in optics was one of the greatest. But isn't it relatively easy to see farther when you are sitting on the shoulders of giants? Just imagine what Newton's contribution would have been if he had been born in the 20th or 21st century. Similar to a multi-faced mirror by Aragon, Michelson used an octagonal mirror, as mentioned in many articles on the internet. However, in his paper published in the Astrophysical Journal, he mentioned that he also utilized mirrors with 12 and 16 faces, made with different materials such as glass and nickel steel. The placement looked like this from a bird's eye view. This is the observation side, where the light source was also present. If the mirror is not rotating, the beam would originate from this place, hit this face of the mirror, and travel on this path to a distant concave mirror kept 35 kilometers away from the place of observation. As we can see here, he chose a much more distant place compared to Fizeau for better accuracy of his measurement. It should also be kept in mind that he was not measuring the speed of light 75 years after the first experiment, but rather he was trying to increase the accuracy. Also, it should be noted that there was another experiment in 1907 which measured the speed of light considering it as an electromagnetic wave based on the proposition made by James Clerk Maxwell in 1865. However, that experiment and another experiment in 1972 were completely based on different methodologies, so we will take those up after this. The light beam would get reflected to a flat mirror after the first interaction with the concave mirror. The flat mirror would again direct it towards the concave mirror, which would then send it back in the opposite direction towards the place of observation. Here, it would hit this face and be reflected to an eyepiece. The idea was that when the mirror is rotating, the place of this second facet would be taken by the facet coming after it in the rotation. If it is not perfectly aligned, unlike the scenarios when it is not rotating, the light would not be visible at the eyepiece. This design shown previously may work in theory but would not work in real life when the mirror is rotating. This previous design is incorrectly claimed to be the setup of Michelson by a few websites and videos. This is probably the reason why Michelson also did not use it. The reason for this is that there will be multiple beams sent by the rotating octagonal mirror like this, and we may not be able to be sure which one actually hit and came to our eyepiece on the other side. The way Michelson resolved this issue was by ensuring that light travels only along this path, and similarly, on its return, it should be able to reach only at one specific angle. In order to accomplish that, he added a few more components at his end. As per the drawing, he utilized completely opposite faces of the mirror. The first face near the light source would reflect to another mirror, which would then reflect again to another mirror placed at the focal point of a concave mirror to make it parallel to the face of the mirror kept near the light source. Here is the hidden genius of this method, which incorporates the functionality of both Fizeau and Foucault, and was beautifully implemented by Michelson. If you recall, Fizeau used a cogwheel to chop the beam of light. In contrast, Michelson achieved the same effect using mirror alignment. If the mirror face is not in the correct position, the light from the beam would not reach this mirror. Since this mirror has two ends, the octagonal mirror still has some freedom to send the light beam to this one. This, in turn, will send it to the other mirror, where Foucault's principle comes into play. In his 1850 experiment, Foucault used a similar concave mirror to reorient the beam coming from a different angle. But Michelson used it to ensure the light beam, even with the slightest deviation, becomes parallel in order to reach this distant mirror only at the correct angle. The path of light here will be the same as described earlier in the previous common explanations. Upon setting on the return journey, it will follow a similar path but in a mirror arrangement. First by reaching the concave mirror, then to another mirror kept at its focal point, then to another one placed near the mirror face close to the eyepiece, and then ultimately reaching this mirror face which directs it to the eyepiece. If the octagonal mirror is not stationary, it would require that the mirror face near to eyepiece be in the exact position. Otherwise, the light beam will not reach it. In the case when the mirror is rotating, this alignment can only happen when one face is replaced by the next face after it. For the octagonal mirror, he observed the light to be at 528 rotations per second for his setup. Let's recap what we observed from Michelson's experiment. Mirrors are incredibly powerful for measuring the speed of light. Also, for better accuracy, one needs to choose between higher rotational speed or longer distance. If you have observed, mirror, mirror on the wall was common in them all. Yes, the common design element in all of the experiments was a distant mirror, which allowed the light source and observer to be at the same location. This also means that all of these experiments measured the time taken for the return journey of the light, which first traveled from a light source to a distant mirror and then returned to the observer after being reflected from the distant mirror. Even Einstein, in his 1905 paper, used the same method by taking the average time of both sides of the journey. This was later seen as a major issue by others, who pointed out that Einstein assumed it to be true by postulating it. In fact, any other value could also be true, because there's a catch. We still haven't been able to measure the speed of light in just one direction, and it has always been measured over a round trip. Thus, the one-way speed of light continues to be considered debatable. In simple terms, the idea was that light can have different speeds in different directions, since we cannot prove it to be true or false through experiments. The idea of different speeds of light in different directions gained popularity with Hans Reichenbach's book, The Philosophy of Space and Time, published in 1928 and translated from German to English in 1957. Reichenbach, in his book, mentioned that the issue was highlighted by E. Mach in The Science of Mechanics, published by the Open Court Publishing Company, Chicago and London, 1919, on page 223. It seems that Reichenbach was focused only on the direct measurement of the one-way speed of light, which cannot be measured without the synchronization of two highly precise clocks. However, this is not a true requirement, as neither Arago, Fizeau, Foucault, nor Michelson used any clocks. They either did it by constraining or observing a visible shift in the position of the returning light beam. In his book, The Philosophy of Space and Time, Reichenbach also claimed Einstein to be wrong. So why did Einstein never bother to correct himself or prove Reichenbach wrong? Many now believe that since we cannot measure the one-way speed of light, this implies that we also cannot prove that the speed of light is the same in all directions, or that light is isotropic in nature. Therefore, even Einstein would have contested him. But even though we have not been able to measure the speed of light in one direction, the fact that the speed of light is the same in all directions, or its isotropic nature, has been proven multiple times. It is not correct to say that Einstein never made a mistake. But the predictions from his earlier version of the theory of general relativity in 1911 were not consistent with what was being observed. He later corrected himself and provided a refined version in 1915, which still holds its ground except in the case of quantum physics. This 1915 version of the theory of general relativity could explain the observed motion of Mercury when it is orbiting nearest to the Sun in 1915 itself. Take special note of the observed motion here, because the actual motion may or may not be the same as what is visible to us due to various effects the light from Mercury is subject to before reaching us. Einstein's theory of general relativity was mathematically confirmed in 1919 during a solar eclipse by an experiment led by British astronomer Sir Arthur Eddington. The key test involved observing the positions of stars near the Sun during the eclipse. According to Einstein's theory, massive objects like the Sun bend the path of light passing near them, an effect known as gravitational lensing. Einstein was not the first to predict gravitational lensing. It had been known for a long time. However, the estimations made earlier using Newtonian physics were half of the observed value. Newtonian physics postulated that gravity was a force that could even affect light, whereas Einstein proposed it as the curvature of space-time. The value of gravitational lensing predicted by Newtonian physics was 0.87 seconds of arc seconds, while Einstein's theory estimated it to be 1.75 arcseconds. During the eclipse on the 29th of May 1919, Eddington's team measured the apparent positions of stars near the Sun and found that their light was indeed bent by the Sun's gravity, matching Einstein's predictions rather than Newtonian physics. This observation provided strong evidence for general relativity and brought Einstein international fame. Then, during the eclipse of the 21st of September 1922, the theory was tested again, and measurements were initially released for 200 stars, and by 1928, data for 3,000 stars had been released. However, there was a small catch. The technology at that time was limited, so the estimations had a probable error of 5%. If we look at the formula of gravitational lensing from Einstein, we see c squared here. The value of this c, as we know, was determined by postulating that light moves at the same speed in all directions, according to Einstein. If you have observed, I quoted two dates for the eclipse. The first is from the end of May, and the second is from the end of September. The months and dates in a year have been defined based on the orbital movement of the Earth around the Sun. During different eclipses, the Earth would be receiving light from faraway stars from different directions. And don't forget to note, this is one-way movement only, from different directions. This technically confirms Einstein's postulation, which is also an assumption. In simple terms, through an experiment. The formula to estimate the precise location of stars involves the value of c, and Einstein postulated that it would be the same in both directions. If that had not been correct, and if the light coming from distant stars had a different speed than he believed, their positions would not have matched what was observed by Sir Arthur Eddington in 1919. Let's assume the light is anisotropic and is just 5% faster in one direction. So what would be the impact on the observations of gravitational lensing, such as from 1922? Would it match? Let's take an example of a cyclist who travels to a point 20 km away and returns. He travels at 10 km per hour speed, which means he takes 2 hours for onward journey and 2 hours for return, making it a 4-hour journey. If he travels by the double of the speed at 20 km per hour during onward journey, then he would be able to cover the onward journey in just 1 hour. So now what should be his return speed if he wants to keep the total time same as of 4 hours? Similar to return journey of light. Remember, we know that the round-tripping time of light is constant. Since he covered the first part at double of the speed, the return journey would not be on half of the speed. Instead, here in return speed, the cyclists need to maintain a speed of 2 by third of the original speed to complete the return journey in 3 hours instead of 2 earlier, and in turn whole onward and return journey in 4 hours. If you want to learn beautiful maths in simpler terms to calculate onward and return speeds while maintaining the same average speed for entire journey, I will create a separate video for that, which you can find in the link given in description. If the light would have been 5% faster in one direction, then it would be about 4.5% slower in the other, similar to the cyclist. This postulation keeps the average two-way speed of light the same, as also highlighted by Reichenbach. By using the same formula for gravitational lensing, if we substitute these values for the value of the speed of light in the formula, the lensing would be 9.8% more in the direction where the light is slower, and similarly 9.3% less in the direction where the light is faster. However, this is not what was observed in the experiments of 1919 and 1922, because the rate of error was relatively low, especially in 1922, where the error bar was less than 5%. So why did Reichenbach ignore the findings of the 1919 and 1922 experiments? These results were available at least from 2 different directions, well before the original publication of his book in German in 1928. Probably what Reichenbach was referring to was the possibility that the speed of light could differ within the error margin of observation, such as by 2%. However, there is no mention of these 1919 and 1922 experiments in his book at all. So, did Reichenbach miss these experiments or intentionally exclude them? We may never know, but he did mention Michelson's 1887 experiment, which aimed to measure the difference in the speed of light in different directions due to the ether wind using his own invention, the interferometer. And now we also know that in 2015, Michelson's interferometer helped detect gravitational waves by observing the difference in the speed of light beams in two different directions in the presence of a gravitational wave. Reichenbach said both Einstein and Lorentz got the interpretation of this experiment wrong in section 31, titled The Lorentz Contraction and the Einstein Contraction, in his book. So didn't Michelson's 1887 experiment itself confirm the isotropic nature of light, or its constant speed in all directions? Since it didn't find any deviations back then, let me know your thoughts on this in the comments. On the thoughts of postulation, how do scientists make such precise calculations for synchronizing atomic clocks to satellite launches and to the exact prediction of celestial events, all of which are based on the theory of relativity? This, in turn, is based on Einstein's convention that the speed of light is the same in all directions. If it had been different in different directions, then satellites, GPS, atomic clocks, eclipse predictions, etc. would not have worked, especially for years without any issues. The reason is that even though the estimation might have been based on the average of the bidirectional or two-way speed of light, their dependent motion has been in one direction. Take out your phone and see that your GPS is always accurate, up to a few meters, irrespective of your location on Earth's surface. And remember, in different places the signal would be coming from a different direction. So just to remind you, the speed of light being the same in different directions has been confirmed, and the issue has only been limited to the estimation of the one-way speed of light using an experiment. In 1907, Rosa and Dorsey took an electrical approach to the problem. They measured the capacitance and inductance of electrical circuits and calculated the speed of electromagnetic waves, essentially the speed of light. It was James Clerk Maxwell who first proved that light is essentially an electromagnetic wave in the 1860s. In 1864, Maxwell published his theory of electromagnetism, summarized in the famous Maxwell's equations. These equations demonstrated that electric and magnetic fields could travel through space as waves, and they predicted that these waves would travel at the speed of light. By measuring capacitance, which is the ability of a system to store charge, and inductance, which is the opposition to changes in current in electrical circuits, Rosa and Dorsey could calculate the speed of electromagnetic waves propagating through those circuits. Since Rosa and Dorsey did not use any mirrors, didn't they already measure the one-way speed of light in 1907 itself? Using Maxwell's equations, which link electric and magnetic fields, they could infer the speed at which electromagnetic waves travel. Their calculations showed that this speed matched the known speed of light from optical measurements. Therefore, their method provided an indirect determination of the speed of light because it relied on electrical properties and theoretical relationships, rather than measuring the time it takes light to travel a certain distance. In essence, it was more like a confirmation. In math, we see that if A is parallel to B and B is parallel to C, then A and C must be parallel to each other. Similarly, since Maxwell mentioned that light is also essentially an electromagnetic wave, and his equations do not rely on any direction for the speed of electromagnetic waves, it also means, by the same logic of math, that the speed of light needs to be the same in all directions. However, they did not measure the time it takes for light to travel a known distance. The calculation of the speed of light was based on the relationship between electromagnetic and electrostatic units, not on the physical movement of light. There was no timing of light's transit between 2 points, which is characteristic of direct measurements. So we will have to give it a pass, though the indirect method allowed for high precision without the technological limitations of direct optical experiments. Personally, I am not sure how to feel about this experiment. I think this deserves more research and consideration from my side, but I do not think it's feasible for me to devote any more time to this. Maybe I will reach back to this on some later day. Finally, in 1972, Evenson and his team gave the most precise estimate of the speed of light, taking advantage of improvements in laser, atomic clocks, and interferometer technologies. Both the 1907 and 1972 experiments were conducted at the National Bureau of Standards, now known as the National Institute of Standards and Technology. This experiment ultimately led to redefining the length of a meter in 1983. The experiment used a methane-stabilized helium neon laser. This laser had an absorption line at 3.39 micrometers, which was highly stable and provided a precise wavelength that could be used as a reference. The interferometer used in the experiment had two highly reflective mirrors and was used to measure the wavelength of the laser light. It allowed the researchers to control the length of the light path, adjusting it to precisely match the wavelength of the laser light. The methane-stabilized laser's frequency was measured using a device called a microwave frequency synthesizer, which precisely generates and controls radio frequencies. This was key because measuring both the frequency and the wavelength of the light enabled the calculation of the speed of light with high precision, using the precise measurements of both the frequency and wavelength of the laser light. The speed of light was found to be 299,792,458 meters per second from this experiment. Before we conclude this experiment on 1972, here is a hidden message for us. Recall that we discussed that in 1983, the definition of a meter was changed to the distance traveled by light in a vacuum in 1/299,792,458 of a second by the General Conference on Weights and Measures. Please note that there are no directions attached to this. This implies that, for all practical purposes, physicists believe the speed of light is constant in all directions. Evidence after evidence from various observations proved the isotropic nature of light, and thus the convention taken by Einstein as a postulate has been confirmed to be an axiom. Just because we could not measure the speed of light in one direction directly earlier, and many still believe that light can be anisotropic, reminds me of people who still believe the Earth is flat. Coming back to the definition of a meter in 1983, I personally think it was a very bad job of defining it, which we again repeated in 2019 when defining a kilogram. Wasn't it our job to simplify things to make them more accessible? In 1960, we adopted the definition of a meter as 1,650,763.73 wavelengths of the orange-red line of the krypton, 86 atom in a vacuum. Mind you, this was based on a suggestion by a Nobel Prize winner, Albert Michelson, who suggested we should use a known wavelength and its finite number of frequencies to define a meter. In 1983, we could have redefined a meter as 1,650,165 wavelengths of krypton 86, which is 606 nanometers. This would have defined the speed of light to be 300 million meters per second, and a meter as the distance traveled by light in a vacuum in 1/300 millionth of a second. But let's leave it with a but here. This was the first video in a series on measuring the one-way speed of light. Does this mean that we are ultimately going to measure the one-way speed of light? Or at least propose a way to do so? Yes, and we will cover that in the fourth video of this series. We will use the insights from the work of all the great scientists mentioned in this video in the fourth episode, so don't forget what we've just learned. But why do we find it difficult to measure in the first place? This is like timing a lightning bolt with a stopwatch. Can you tell when the lightning struck? Was it when we saw it? Or when we heard it? We hear the sound of lightning a few seconds later because light travels faster than sound. But it's also incorrect to say that the lightning occurred exactly when we saw it. For example, light takes about 8 minutes to reach us from the sun. So if we see a solar flare, it actually happened about 8 minutes earlier, not when we saw it. Measuring the one-way speed of light has been an interplay of three sides of a golden triangle: inertial frame of reference, simultaneity, and time dilation. We will discuss their interplay in our next video. We will also cover 10 evidences of the same speed of light in all directions in this video series, after discussing our golden triangle in the second video. Hope you enjoyed this one.